When we talk about the mass of an element, we need to remember that most of an atom's mass comes from its nucleus, in which the protons and the neutrons are located. When determining the mass of just a single atom or a small quantity of atoms, instead of using grams, which would be too large of a unit to use for this magnitude of mass measurement, we use the units atomic mass units, which are abbreviated by the letter U. And one atomic mass unit is defined as 1/12 the mass of a single carbon-12 isotope atom. When we look at the periodic table and we find the atomic mass that's listed on the periodic table, or the atomic weight, we notice that very rarely, if ever, are those numbers whole numbers. And so the reason for that is, one, remembering that we usually treat the proton and the neutron as having a mass of 1 AMU, although it is slightly different than that. But for all intents and purposes, it would round off to 1 AMU. But also the thing to remember is that the masses that are listed on the periodic table are not for one single atom of that particular element. It's actually an average mass that includes all of the isotopes for that given element. And it's a weighted average, meaning that it depends not only on the mass of the particle itself, but also on its percent abundance. You recall that isotopes are atoms of the same element, so they behave chemically the same way, have similar physical properties. Their main difference is their mass. Some isotopes are heavier than others. That mass difference is due to differences in the number of neutrons in each nucleus. How these abundances are measured, how abundant one isotope is versus another, is determined using an instrument known as a mass spectrometer, which takes a sample and ionizes the sample, and the different particles that are produced based on their mass, they pass through a magnetic field, and due to their inertia, their trajectories based on their mass and that magnetic field will change accordingly to their mass, and their paths will be different from one another. And so depending on how heavy the particle is will determine how much the path of that particle is altered, and thereby you can determine out of a given sample how many particles have their path deflected the most versus those that are deflected the least. And in that way you can calculate what percent of your element is the heavier isotope and what percent is the lighter isotope. So if we take, for example, chlorine. Chlorine has two main isotopes, chlorine-35 and chlorine-37. And the percent abundances are, as you see here, 75.78% chlorine-35 and 24.22% chlorine-37. Now, the first step in order to determine the average atomic mass of this element is to take the percent abundance times the mass number for each isotope. Once you get those numbers, then you want to add these up. Now, before we do any math here, if we simply use our powers of estimation, we see that the majority of the chlorine atoms, 3/4 of them, have a mass of 35 as opposed to a mass of 37. So if we were to predict what our answer should be, we should be at the very least predicting that our answer should be closer to 35 than it would be to 37. So that gives us a ballpark estimate for comparison when we actually get our answer to see if it's reasonable or not. Back to the problem at hand, if we take the mass number of each element times its percent abundance, please note that you move the decimal point 2 places to the left when multiplying by a percentage, so 0.7578 times 35 AMU, and 0.2422 times 37 AMU. That's going to give us 26.52 AMU for the first isotope and 8.961 AMU for the second isotope. Notice that we do round off for significant figures each step, because at first we're dealing with multiplication, now we're dealing with addition, and the two rules differ. When we add, you should come up with 35.481 atomic mass units. Rounding off properly for sig figs, we would cut our answer off at the hundredths place, and therefore your final answer for the average atomic mass of chlorine is 35.48 AMU.